Dear students, welcome back. So, for the previous two lectures, we are doing real numbers. So, in the previous lecture, I told you about LCM and SCF, and I told you about fundamental theorem of arithmetic. So, today we'll do a few examples based on LCM and SCF, and then we'll continue with the topic. Today I'll tell you a few points regarding rational numbers and irrational numbers. But before that, we'll start with today's example. And the question is, there is a circular path around a field. Sonia takes 18 minutes to drive one round of the field while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction and go in the same direction, then after how many minutes will they meet again? At the starting point. At the starting point. Now see, the question says that there is a circular path around the field. Now Sonia can drive one round of that path in 18 minutes, whereas Ravi can do the same in 12 minutes. That means Ravi is driving faster than Sonia. Now they start at the same point, at the same time, and in the same direction. So now they are saying after how many minutes, after how much time they will meet again at the starting point. Now see, suppose this is the circular track. Okay. Now Sonia and Ravi both start at this point and they move in this direction. Now Ravi completes the turn in 12 minutes and after 12 minutes Ravi is again here. But as Sonia takes 18 minutes to complete the full round, so at 12 minutes Sonia may be here. Then after one more round, that means after 24 minutes again Ravi is there, but obviously Sonia will be lagging. Now we have to calculate after how many minutes both of them will be together again at this point. That means you have to find the the number, because the question says that after how many minutes will they meet again at the starting point. That means you have to find a number which is exactly divisible by 12 and 18, because if a number is exactly divisible by 12 and 18, that means that the say x is that number. So x, in x minutes, Ravi will take complete number of turns and Sonia will also take complete number of turns. So you will the both of them will be here at the starting point together. So the solution says find a number which is exactly divisible by both 12 and 18. So find the LCM of 12 and 18. So you have to find the LCM, least common multiplier of 12 and 18. Now you know that 12 can be written as 2 into 2 into 3, and 18 can be written as 2 into 3 into 3. Okay. Now the LCM will be, the highest power of 2 here is 2 and here it is 1. So we will take the highest power, that is 2 to the 2. You know, while finding out the LCM we take the highest power. Now here the power of 3 is 1, here the power of 3 is 2. So we will take power of the power of 3 as 2. Now 2 square is 4 and 3 square is 9, and that is equal to 36 minutes. So your answer is that both of them will meet again at the starting point after 36 minutes. And it is logical also, because if Ravi takes 12 minutes to complete one round of the field, that means in 36 minutes Ravi will make 3 complete rounds, and as Sonia is taking 18 minutes to do to complete the round, that means in 36 minutes she will take 2 complete rounds. So they will be again together at the starting point after 36 minutes. That is your answer. Clear? So the next example for today. Next example, explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Now before doing this question, I hope all of you know about prime numbers and composite numbers. Those numbers which have only 2 factors, that is the 1 and the number itself, they are called the prime numbers. I repeat, those numbers which have only 2 factors, that is 1 and the number itself, then they are called prime numbers. For example, 2, for example 3, 5, 7, 11, they are all prime numbers because they have only 2 factors, 1 and the number itself. And if any number has more than 2 factors, then it will be a composite number. Now you have to show that these numbers are composite numbers. So if you take the first number, which is 7 into 11 into 13 plus 13, it's very clear. You can see that 13 can be taken as common. So if you take 13 common, so within brackets you will have 7 into 11 plus 1. Now 7 into 11 will be 77 plus 1 is 78, and now you can see at least two and the third number is 2. So 3 factors are there, which shows that this given number is a composite number. This 13 into 78, it will be a composite number. Okay, because 1 is definitely a factor and 13 and 78 are the factors, so it's a composite number. Now the second part, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Once again you see we can take 5 common. 5 is there and 5 is here, so we can take 5 common. If you take 5 common, then within brackets we'll have 7 into 6 into 4 into 3 into 2 into 1 plus 1, because I have taken 5 common. Now you see 3 into 2 is 6, 6 into 4 is 24, 24 into 6 will be 144, and 7 into 144 plus 1, that is once again you see it is 1009 into 5. So 1 is definitely a factor, and then 5 and 1009. Once again we have 3 factors, so it is also a composite number. So it is also a composite number. Clear? Now see, these are the examples based on the previous lecture. Now today I will tell you something about rational numbers and irrational numbers. Rational numbers. If a number can be expressed in the form of P upon Q. If a number can be expressed in the form of P upon Q, where P and Q are integers, but Q is not equal to 0, then it is called a rational number. So I repeat, if a number can be expressed in the form of P upon Q, where P and Q are integers, but Q is not, although 0 is an integer, but Q should not be equal to 0, then it is called a rational number. And definitely a number which is not rational number is called an irrational number. If a number is not rational, then it is called an irrational number. Irrational number. A number which cannot be represented in the form of P upon Q, P and Q being integers, then it is called an irrational number. Clear? So any number which is not rational will be called an irrational number. Now if we see a few examples of rational numbers, like say there is a number say 27. So you know that 27 can be written as 27 upon 1. Now 27 upon 1, P upon Q, 27 and 1 both are integers. So definitely it is a rational number. Okay. One more example, minus 3. You know minus 3 can be written as minus 3 upon 1. Once again you see minus 3 upon 1, P upon Q, minus 3 is and 1 both are integers. So it is definitely a rational number. Now another say 7.2. Now 7.2 can be written as 72 upon 10 if you remove the decimal. You can cancel it by 2. Now you see 7.2 is actually 36 upon 5. Excuse me. 36 upon 5, P upon Q. Both 36 and 5 are integers. So definitely this is also a rational number. Clear? Now one very important thing. Suppose 0 is there. Now you know that 0 can be written as 0 upon 1. Now 0 upon 1, P upon Q, both 0 and 1 are integers. So according to the definition, it should be a rational number, and 0 is a rational number. So always remember 0 is a rational number. So now you may think that in this way all the numbers are rational numbers, but square root of non-perfect square numbers, they are all irrational numbers because they cannot be represented in the form P upon Q. Like say root 2, root 3, root 5, root 6. They are all irrational numbers because they cannot be represented in the form of P upon Q. Clear? So I'll explain further how these numbers are irrational numbers. Before that, it is clear to you, rational and irrational. Now I'll tell you something about terminating, non-terminating but repeating, and non-terminating, non-repeating decimals. Now see, terminating, non-terminating decimals. Terminating and non-terminating decimals. Now first of all, suppose 351 upon 40. There is a ratio 351 upon 40. Now 351 upon 40, P upon Q, both are integers. So according to definition, this is nothing but rational number. Definitely it is a rational number. I hope it is clear to all of you that it is a rational number. Now we will divide. Simply divide 351 by 40. Now we divide 351 by 40. So I think it will be 8 times. Now you see the value we are getting is 8.775 and no remainder is there, so we have to stop the division here. So this is a terminating decimal. You see that the decimal has terminated, it stops, so it is terminating decimal. Terminating decimal. So we have proved that terminating decimals are all rational numbers, because this was a rational number and I have shown you that it is terminating decimal. So terminating decimals are rational numbers. Okay. Now I will take one more example. Now I will take 65 upon 12. Almost the same thing I have taken. Again you can see 65 by 12, my means it is P upon Q form. Both 65 and 12 are integers. So by the definition this is also a rational number. Okay. So this is a rational number. The definition of rational number says that this has to be a rational number. Now we'll divide it. So you divide 65 by 12. You divide 65 by 12. Now you can see there is a very interesting thing. Now the remainder will never be 0. It will be 80 again, and in fact 8, and when we add 0, so we will get 5.416666, and this 66 goes on to infinity. So they are called non-terminating repeating decimal. Okay, the value is 5.416 and just put a bar on 6, which says that the 6 is repeated again and again. When the bar is only on 6, that means 6 will be repeated again and again. So this is called non-terminating repeating decimal. So see, 65 by 12 was a rational number and it comes out to be non-terminating repeating decimal. That means terminating decimals are rational numbers and non-terminating repeating decimals are also rational numbers. I repeat, terminating decimals are rational numbers and non-terminating repeating decimals are also rational numbers. Now, suppose you are finding out the square root of 2 by long division method, or square root of 3, or square root of 5, 6, square root of 12, square root of 15, any number, any non-perfect square number. If you are finding out the square root of that number, you will get non-terminating, non-repeating decimal. Okay, you will get non-terminating, non-repeating, means the decimal is never terminated and it is not repeating also, and in that case it will be irrational number. So always remember, terminating decimals are rational numbers, non-terminating repeating decimals are also rational numbers, but non-terminating, non-repeating decimals are irrational numbers. I will give you an example. Say 5.41, 411, 4111, 41111, 4, and so on. So you can see, first we have one time, then 2 times, 3 times, 4 times. That means it is not repeated. It will never, if you just, it goes on increasing the number of ones there, so it will never repeat it, and it is not terminated also. So non-terminating non-repeating decimals are irrational numbers. So I repeat, whenever you find the square root of a non-perfect square number using long division method, you will get a non-terminating, non-repeating decimal, and that is irrational. That is why the square root of all the non-perfect square numbers are irrational numbers. Is it clear? Now, this is rational, this is also rational, but this is terminating and this is non-terminating but repeating. Now, without dividing, how will you find that the given fraction will be terminating or non-terminating, repeating? My question is, suppose a fraction is given to you. Without actual division, how will you find whether the given fraction will give you a terminating decimal or a non-terminating but repeating decimal? And now there is a technique of that. I'll tell you what is the technique. In the given fraction, you just take the denominator and find the prime factors of the denominator. I repeat, in the given fraction, find the prime factors of the denominator. So here the denominator is 40. Now find the prime factors. 2, now listen carefully. When you find all the prime factors, if the prime factors are only 2 or 5 or both, here 2 and 5 both are there, either only 2 or only 5 or both, means the prime factor should be only amongst 2 and 5, then it is terminating decimal. Okay, if the prime factors of the denominator are among 2 and 5, then it is terminating decimal. So you can see here, when we find the prime factors of the denominator, it is only 2 and 5. That is why it is terminating decimal. And if any other prime factor is there other than 2 or 5, if any one prime factor other than 2 or 5 is there, then it will be non-terminating but repeating decimal. If only 2 or 5 is there, then it has to be terminating decimal. If any other prime number is there other than 2 or 5, then it will be non-terminating but repeating decimal. For example, say 12 is there, so you take 12 here and find out the prime factors. So you can see here we are getting 3 as the prime factor. So it is non-terminating but repeating. Clear? If in the prime factors of the denominator we have only 2 or 5 or both, then it is terminating decimal. In the prime factorization of the denominator we get any other factor other than 2 or 5, then it will be non-terminating but repeating. And whenever you find out the square root of a non-perfect square number using long division method, it will be non-terminating, non-repeating, and that is why it is irrational. Okay? Now, I'll give you one theorem. let P be a prime number. P be a prime number if P divides A square, then P divides A. Where A is a positive integer. Okay, the theorem says let P be a prime number. If P divides A square, then P divides A also. P is any prime number. Now P divides A square, any perfect square number. Then P will divide the square root of that number, means A also, where A is any positive integer. Now I'll give you the proof also. Let A is equal to P1 into P2 into P3 into P4 so on till Pn, where P1, P2, P3, P4 so on Pn are prime numbers. They are prime numbers. Now, in the previous lecture, I told you the fundamental theorem of arithmetic, which says that any positive integer can be represented or can be expressed as the product of various powers of prime numbers. So here also, as A is a positive integer, then A can be represented as the product of prime numbers. So A is equal to P1, P2, P3, P4 up to Pn. These are the prime numbers, and they definitely few of them may be same also, because they can be powers of prime numbers. So, but they are all prime numbers. Okay. Now, if A is on squaring both sides, A square will be equal to P1 square, P2 square, P3 square, P4 square, so on till Pn square. Okay. P is a prime number which divides A square. P is a prime number which divides A square, the theorem says. That means P has to be one of these. P is one of P1, P2, P3, P4, Pn. Okay, so you can see if P is a prime number which divides A square, but the A square has these factors, so P is one of P1, P2, P3, because P1 square, P2 square, definitely they are not prime numbers. P1 is a prime number, but P1 square is not a prime number. So P is one of P1, P2, P3, P4 up to Pn. That means P is one of these factors, so P is a factor of A, so P divides A also. Therefore, P divides A also. So we have proved that when P divides A square, then P divides A also. Clear? So the theorem says that if P is a prime number and P divides A square, then P divides A also. Clear? Now it's a very important theorem. Using this theorem, we will do few questions. Like the first example. Prove that root 2 is an prove that root 2 is an irrational number. Although I have told you that the square root of any non-perfect square number is an irrational number, but here you have to prove that root 2 is an irrational number. Now what we do? We do this question by the method of contradiction. Let root 2 is a rational number. We assume that root 2 is a rational number. Let root 2 is a rational number. We have assumed that root 2 is a rational number. Now by the definition of root 2, by the definition of rational number, we can say root 2 is equal to then root 2 is equal to P upon Q, where, or you can say root 2 is equal to R upon S, where R and S are integers. You know that is the definition of rational number. If root 2 is a rational number, then root 2 will be equal to R by S, where R and S are integers. Now what we do, we just cancel out the common factor in R and S, and after that suppose we get root 2 is equal to P upon Q. Now after simplifying R by S, we are getting P by Q, so that means P and Q have only one common factor, that is 1. P and Q have only 1 as the common factor. I hope it's clear. First of all, we have taken root 2 is equal to R by S. Now R and S are integers, but they may have few common factors. So we cancel those common factors, and then we have root 2 is equal to P upon Q. That means in P and Q we have only 1 as the common factor. Now what we do, if you cross multiply P is equal to root 2Q, squaring both sides, squaring both sides, you will have P square is equal to 2Q square. So Q square is equal to P square by 2. As you know, P and Q are integers, so Q square is also integer, P square is integer, so P square is divisible by 2, or 2 divides P square. 2 divides P square. So 2 divides P also. So I have proved in the previous topic, I just shown you that when P divides A square, then P divides A also. So here 2 divides P square, so 2 divides P also. So P is equal to 2M. Now here you put P is equal to 2M. That means Q square is equal to 2M whole square upon 2, 4M square upon 2, that is 2M square. That means M square is equal to Q square by 2. Once again you see M is an integer, so M square is also an integer, Q square is an integer. That means Q square is divisible by 2, or 2 divides Q square. 2 divides Q square. So 2 divides Q also. So Q is equal to say 2N. But now one thing, P has a factor 2 and Q also have a factor 2. But here they say that P and Q have only 1 as a common factor. So there is a contradiction. Clear? So 2 is common, 2 is a common factor of P and Q. It contradicts our assumption, so root 2 is an irrational number. We started by assuming root 2 is a rational number. Then the result that we are getting, it contradicts, because midway we said that P and Q have only one as the common factor. At the end we are getting that 2 is also a common factor of P and Q, which means that our assumption in the beginning was wrong. Root 2 is not a rational number, but it is an irrational number. Clear? Now I'll tell you few more theorems. The sum or the difference of a rational and an irrational number is irrational. Okay, so the sum or the difference of a rational and an irrational number is irrational. If you are adding a rational number and an irrational number, you will get an irrational number. Or if you are adding a rational number, if you are subtracting an irrational number from a rational number, you will get an irrational number. Now, theorem 3 is the product and quotient of a non-zero rational number and an irrational number will be irrational. Okay, so the product and quotient of a non-zero rational number and an irrational number will be irrational number. Now I'll give you one question, one example. Show that five minus root 3 is irrational. So this question also we'll do by the method of contradiction. Let 5 minus root 3 is a rational number. Five minus root 3 is a rational number. Then 5 minus root 3 is equal to P upon Q. 5 minus root 3 is equal to P upon Q, where P and Q are integers. You know that. So 5 minus P upon Q is equal to root 3. If you change sides, 5 minus P upon Q is equal to root 3. That means 5q minus p upon q is equal to root 3. Now you see, p and q are integers, 5q is an integer, p is an integer, integer minus integer will be an integer upon integer. So it is nothing but a rational number, but we know that root 3 is irrational. That we just proved that root 2 is an irrational number. Similarly, we can prove that root 3 is also an irrational number. So there is a contradiction. The left hand side is clearly rational, whereas right hand side is irrational. So in the result, left hand side is rational, whereas right hand side is irrational. So it contradicts our assumption. So 5 minus root 3 is irrational. Okay? Is it clear to everybody? We started with the assumption that 5 minus root 3 is rational, but the result that we are getting is not correct. The left hand side is rational and the right hand side is irrational. That means our assumption at the beginning is wrong. So 5 minus root 3 is not a rational number, but it is an irrational number. Clear? So with this we have proved this topic, real numbers. Do all the questions given in the assignments and in your textbook, and in the next lecture we will start a new topic. Thank you.